Today, we start looking at rational functions and graphs. We're going to start out by reviewing what we saw with the rational function with our parent function that we studied at the beginning of the course. And so if you recall, our rational functions, which are going to be of the form like f of x equals 1 over x, they'll have two different branches to them. So if we just do a quick sketch, again, we had one branch that was hitting at the point 1, 1, and was in the first quadrant, and another branch hitting at -1, -1 in the bottom left or the third quadrant. So we can also use the same transformational form that we talked about before. We're not going to see this as often, so let's just do one quick example and a reminder of the rules, because we are going to see a lot more functions with this unit that have everything in their standard form. And so we need to look at how we can find some of these same properties when we're given a function in that different format. So first off, if we are dealing with transformational format, we still have our a value, our h value, our k value, and they still do the same things overall to our picture. So in the transformational form that you see at the right, we may see a value in for a in the numerator of the fraction. And again, as before, that's going to say whether or not we're kind of in the regular orientation. So we could say regular orientation. In other words, the branch up to the right and the branch down to the bottom. Or if we had a negative value there, then we're going to flip things vertically. So flip vertically. We could also talk about what happens when that is a value other than 1 or positive or -1. If we have something that's greater than 1, like a 2 or a 4 or what have you, just like we did before, that's going to be a stretch, which again is going to be in the vertical direction. So instead of the point being at 1, 1, the point might be at 1, 2 for a stretch of 2 or 1, 3 for a stretch of 3. If our value is between 0 and 1, so a number smaller than 1, which we wouldn't see too often because we don't typically have a fraction inside a fraction, but that would mean we have basically a compression. We've talked about this in terms of a shrink, but I like to think compression when I'm talking about that because we're kind of squeezing things down towards the x-axis. And again, both of these would be in the vertical direction. We also have our h and our k values that work the same way as they did before. And so our h, it's kind of inside our function in that it's in with the x in the denominator. And so if we had a positive h, again, don't forget that moves our entire function to the left or the picture to the left. A negative h would move everything to the right. And then our k value, which is outside of the fraction, outside of the rational expression, a positive k would move everything up and a negative k would move everything down. And so right now, all we've talked about before are asymptotes. So let's see what that looks like in an example. And then we'll start pulling in a new piece of vocab and see how our equation, how we can figure out what that is without necessarily relying on graphing this out on Desmos or a graphing calculator. So let's look at example 1 first. So here we go. Example 1, we're going to graph and describe the function g of x equals 1 over x minus 2 plus 3. So again, I want to keep in the back of my brain, my points usually are at +1, 1 and -1, -1. So with this, our horizontal asymptote, again, that was the imaginary line that we don't usually cross, aka in our general parent function, that's the x-axis. But if we have this +3 on the end, that means we're going to move our whole graph up 3. So that means we would have a horizontal asymptote at +3. Again, an imaginary line that we can't cross. So that's why if I draw it in, I'm always using dotted lines. And then we have our -2. Actually, let's go ahead and write that down first. So our horizontal asymptote moved up 3. So keep in mind, if that's a horizontal line, that's always going to be y equals 3. Keep that in the back of your brain. Our vertical asymptote, well, again, usually it would be right at that y-axis. But because of this -2 that's in the denominator, again, that means we're going to move our graph to the right 2 units. So that vertical asymptote is going to move right 2, which means we will have a vertical line at x equals 2. Again, an imaginary line that our graph cannot cross. So that means 2, since we don't have any value up in the a at the top of the fraction, I know I'm going to have one of my points up 1 and over 1 from where my asymptotes cross. And our graph is going to be up in that top right portion. And then the other branch of our graph would be, again, left 1 and down 1 from the center of where our asymptotes meet. And there's our other branch. And so when we think about domain and range, and we'll look into this a lot more next class when we look at characteristics in general of all rational functions. And so we'll put together what we look at today, and we will pull back in our domain, range, increasing, decreasing intervals, and all of those properties. Right now, let's just think about our domain and our range. Well, in our horizontal and vertical asymptote, again, we have a value that we cannot cross. So domain, if we're thinking about our x values, well, our vertical asymptote is at x equals 2. In other words, that's the imaginary line I cannot cross. Therefore, x cannot be equal to 2 at any point in this function. If I plug in a 2, look at the bottom of your, or look at the denominator of the rational part of that function. Well, if I plug in a 2, that's going to make the denominator 0. And right off the bat, I'd get an undefined message if I tried to plug that in the calculator. So it does not exist. And so along the same vein, if I tried plugging in a 2, then the problem is I have that undefined message. And so whatever answer I would get out, I'm going to call range actually g of x, because that's what our function was named. Our g of x cannot be 3, because again, it cannot cross that line. We cannot get an answer out of 3 any other way other than trying to get that. We'd end up with that undefined fraction for the first piece. So again, we're not going to see these too often, but they still follow the same format as when we did all the other transformational forms, our vertex form of quadratics, graphing out our absolute value functions. They all are using those same patterns. But now let's look at one extra piece on here. So when we deal with rational functions, not only can we have asymptotes, but when we start introducing additional expressions or additional components to that function, we have something called a hole. So again, an asymptote is a discontinuity where our graph cannot cross that imaginary line. A hole is a specific point on our rational function where the graph just doesn't exist. The function doesn't exist at that number. And the reason we have those is because as we look at these functions in different formats, we're going to have factors and expressions that go kind of above and beyond that transformational form. So let's look at a few of these and see, well, how could we find this information? Now, side note at this point, if you are not quite comfortable with factoring still, I would absolutely suggest going back to Unit 3 and reviewing especially the difference of squares and factoring trinomials, as we're going to be doing that a lot this unit. Alrighty, so usually with the functions we're going to look at, and this is the lion's share of what we're going to see in this unit, we will look at functions that are actually written out in standard form. So in other words, all of the values are all multiplied out, and we're dealing with trinomial expressions or binomial expressions. And so there's 3 phases to actually finding where these discontinuities are that will enable us to actually draw these out. So first, we're going to figure out where the horizontal asymptotes are. So where are the vertical lines that we cannot cross. And we have 3 scenarios where this is going to happen. So we figure these out by looking at the degree in the numerator and denominator. So again, don't forget, degree is your highest exponent on any term, or how many factors you have in that expression. Now, when we have things written out in standard form, easiest to just look for what's the highest exponent. So in example 2, we have our function 2x minus 5 over 3x squared plus x minus 3. So looking at our degrees, well, the numerator, he has a degree of 1. Highest exponent is just that plain x, or the 2x, which has an exponent of 1. Your denominator actually has a degree of 2 because we have an x squared. So the degree of the numerator is less than the degree of the denominator. When we have that scenario, we're going to have a horizontal asymptote, which I'm going to abbreviate as HA. Our horizontal asymptote is always going to be y equals 0. And again, you could always graph this out on Desmos calculator to double check. And in fact, if you don't believe me on this one, pause the video or go back and graph that on Desmos after we've checked out these examples. Okay, our second scenario is, well, again, let's look at our degrees. Well, our numerator has a degree of 3. Highest exponent is 3, but it's the same thing in the denominator. So the denominator degree is also 3. So in this case, this scenario, the degree in our numerator is equal to the degree in our denominator. When that happens, what we're going to do is divide our leading coefficients. In other words, the constant that's right in front of that x cubed, let's just make a fraction with that. So that means in this scenario, our horizontal asymptote is going to be y equals 5 over 3, because again, I'm just using the 5 and the 3 that are the leading coefficients in my expressions. Alrighty, then our third scenario, well, we did numerator was less than, we did numerators equal. So in this last one, our numerator is greater than. So again, looking at our expression, degree in our numerator is 4. Degree in the denominator is 1. When this happens, we actually do not have a horizontal asymptote. So no horizontal asymptote. And again, if we were to graph this out, you would see that the shape of this looks a little bit strange, and we'll see more example of those next class, and you can experiment on your own in Desmos. But, you know, the rational functions, yes, our general shape is going to look like our 2 branches, like we just did in example 1. But sometimes we're going to have additional pieces that come out with, you know, the different factors and the different pieces that go into our expression. Alrighty. So that's how we find our horizontal asymptotes. So phase 2 in figuring out all of our discontinuities is now we're going to look for those holes. So again, a hole occurs when we try to plug in a value and it doesn't exist in the function. Things fall apart. We may have, you know, an undefined expression when we try to plug that in. And so let's see what happens with those. So to find the holes in any rational function, first thing we're going to do is factor the numerator and the denominator completely. This is where your factoring comes in. For holes, we're looking for where do we have matching factors. In any expression where you have the same factor in the numerator and denominator, you will have a hole at that, basically that intercept, kind of like how we figured out with quadratic functions. We set each factor equal to 0 and solved it out. We're going to do the same thing to figure out where our holes are. Then we always want to know exactly where that point's going to be. So we'll take that x value that's at our hole, and we will plug it back into any remaining factors to see what those would simplify out to if we ignored the factors that gave us the hole. So in example 5, well, first off, let's go ahead and think about that horizontal asymptote before we do anything else. So in this one, just to practice what we already had, horizontal asymptote, well, our degrees are exactly the same. So that means we're going to have a y equals 1. The leading coefficients on both of our expressions are 1. Alrighty. So now let's look at factoring this out. So our numerator factors out to x plus 2, x minus 2, excuse me, plus 2, because we're trying to get that positive 4 at the end. A positive 4 is our middle term, and those will multiply out. In our denominator, let's see, to get a 14, we're probably going to need a 2 and a 7. And to make that into a -5, we can do a positive 2 and a -7. And so you'll notice we have a common factor, x plus 2, in the numerator and denominator. So when that happens, that's when we're going to have a hole. So our hole we can find by just setting that factor equal to 0 and solve for x. So we have a hole at x equals -2, but we need to know what the y coordinate is so we could actually find this on a graph. So we're going to take our remaining expression and we're going to go ahead and plug in that x value that we know doesn't exist for the rest of that function. So we'd have a -2 plus 2 and a -2 minus 7, aka a 0 over -9, otherwise known as 0. So our hole is going to be at the point 2, 0. So we'll actually have an empty place in that function. And you'll see how we sketch this a little bit later on and with our next video. Alrighty, example 6. Again, let's predict our horizontal asymptote first. We have degrees that are exactly the same. So again, looking at our leading coefficients is how we'll find that when our degrees are the same. Both of them are 1 again. So again, our horizontal asymptote on this would be y equals 1. Let's find the holes. So now, again, let's factor. So numerator factors out to x plus 2, x plus 3. Denominator, difference of squares. So that's an x minus 3, x plus 3. Again, the order you write the factors in doesn't matter, but as I was writing that out, I noticed, wait a second, I'm going to have an x plus 3. We have a common factor, numerator and denominator. So I know we're going to have a hole. And that hole is going to occur when x plus 3 equals 0, aka x equals -3. Again, if I plug that -3 into that factor, well, the problem is in the denominator, that would create a 0, and we can't divide by 0. That's undefined. So again, let's test where's that going to leave us with a y coordinate on that 0. So we know where this thing is placed. Plug it into x plus 2 over x minus 3, our remaining factors. So -3 plus 2 over -3 minus 3, aka a -1 over -6, or just 1/6. So our hole is actually at -3, 1/6. All right, and you might ask, well, why am I bothering to find these algebraically when we have Desmos as a graphing calculator? Keep in mind, these are points, and the asymptotes, imaginary line that we can't cross, they don't exist in the function. So they will not be actually graphed on that Desmos graphing calculator. And if you try this on a TI calculator, you're going to have some things going a little bit wonky. Sometimes it almost looks like it's graphing that asymptote, but it's really just the computer having difficulty with the fact that you've got an undefined value, and the graphing calculator, not a very powerful computer, but it is a computer. And it just has difficulty drawing those two different branches and figuring out what's going on in between them. And so we still need to know how to find these algebraically so we can predict where they are in the graph. Alrighty, so our last piece is we need to look at, we found horizontal asymptotes, we found holes. The last piece is the vertical asymptote that we would expect to have in the middle of most rational functions. So let's see how we can attack that. And so we're going to put it all together. So all asymptotes and all holes on these expressions. Your vertical asymptote, after you've found your horizontal, after you've found your zeros, if you have any additional factors left in your denominator, that's when you're going to have a vertical asymptote. So here we go. So wait a second. Example 7. Again, we know our numerator actually has a degree of 0. There's no x value in there, so it's just a constant. So again, because the numerator degree is less than the denominator, that's our scenario where our horizontal asymptote is actually going to be y equals 0. So that's our imaginary line we can't cross. Okay, next up, let's factor. Okay, nothing to factor in the numerator. However, our denominator, we could factor it out as x minus 5 and x plus 4. So that tells me I don't have any repeated factors. So that means I'm going to have no holes on this one because there's no repeats. So then our third thing to think about is our vertical asymptotes. So your vertical asymptotes, those are going to happen anytime you have any leftover factors in the denominator. We haven't done anything with either one of them. So both of those are going to yield a vertical asymptote. So for both of these, just like with the holes, I need to set the factor equal to 0 and solve for x. So I'm going to have a vertical asymptote at x equals 5 and a vertical asymptote at x equals -4. In example 8, this one I can do some more factoring. But again, if I want to go in order of our 3 stages, let's look for our horizontal asymptote first. Again, we have a degree of 1 in the numerator and a degree of 2 in the denominator. So the numerator is less than the denominator. So in other words, our horizontal asymptote, same scenario, y equals 0. 2 is greater than 1. Alrighty, let's factor this out and see if we have any holes. So numerator is going to stay as an x minus 7. And again, you don't have to put it in parentheses, but I like to. X squared minus 49 is perfect square. So x plus 7, x minus 7, excuse me, our difference of squares. And we have a common factor of x minus 7. So that's where we're going to have a hole. So our hole is going to occur when x minus 7 is equal to 0, makes our equation fall apart. And finding where that's going to be when we plug that in. Again, we're left with 1 over x plus 7. So plug in a positive 7 and we get 1 over 14. So our hole is going to be at 7, 1/14. So over 7, but really, really close to that x-axis. We do have a leftover factor in the denominator, so that means we're going to have a vertical asymptote. And that's going to happen where we have that x plus 7. X plus 7 cannot equal 0. It would be undefined. Therefore, a vertical asymptote happens at x equals -7. So our last thing to do, let's put those all together. So let's take our information about horizontal asymptotes, holes, vertical asymptotes, and let's kind of kick back to finding our x and y intercepts and actually start sketching these graphs. Now we're going to get a lot more practice with this next class as well. And don't forget, you can always check things on your Desmos calculator, but that's only going to give you your general shape. You will have a chance you can check your x and y intercepts as well, but it won't tell you exactly where there's holes and asymptotes are. Always need to do the algebra behind it. All right, so our last 2 examples, here we go. Let me shrink my screen down a little bit. All righty. So again, in order, first task, horizontal asymptote. Look at your degrees. Our numerator is greater than our denominator. Therefore, we are going to have no asymptote. So there's none. Our numerator is greater than our denominator. Alrighty, now let's factor. Oops. So numerator factors to x plus 5, x minus 2. Denominator is still at x plus 5. So we have a repeated factor. So we will have a hole. So our hole is going to be at, let's see, x plus 5 equals 0. So x equals -5. Plug it back in to find where that hole will be. And so again, that's going to be x minus 2, aka -5 minus 2, or -7. So our hole is going to be at -5, -7. Do we have any vertical asymptotes? No leftover factors in the denominator, so no vertical asymptote on this one. Wait a second. Rational functions are supposed to have a horizontal and a vertical asymptote. But let's think about this. Our x plus 5 kind of canceled itself out. We're left with just a plain old x minus 2. So in other words, f of x, when we simplify everything out, equals x minus 2. Wait a second. That's just a line. I know the line x equals, or excuse me, y equals x minus 2 is going to have a y-intercept of -2 and a slope of 1. So I can just go straight up to the right. There's my other x-intercept. I don't even need to do the math behind them to find that. But then as I continue down, again, I'm going to have a hole. The graph does not exist at -5, -7. So wait a second. So -5, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, right at the bottom of the graph. I'm actually going to have a hole. So I'm going to draw in an open circle to say I can't actually go through that point. But if I continue graphing my line, I'm supposed to hit that point. But because this is a rational function, that's what means, or that's what's giving us, hey, we have this missing piece because we have those rational expressions that simplified out. And then we're left with just that line. So if you were to graph this on Desmos, it will look exactly like a line. Again, your original function graphed on Desmos. But if you tried clicking on the point -5, -7, it's going to say it's undefined or does not exist at that point. Let's look at one more. And again, don't forget, I don't expect you to be able to sketch these out perfectly yet. We are absolutely going to be looking at more of these with practice with our discontinuities and all of our characteristics. We'll be pulling all those together next lesson. Alrighty, so example 10, last one. Horizontal asymptote. Well, our numerator and denominator degrees are equal. Therefore, that means we need to look at our coefficients. We have an implied coefficient of 1 in the denominator. So that means our horizontal asymptote is y equals 2. Now let's factor to look for holes. Okay. We can factor a 2 out of the numerator, leaves us with an x squared minus 1. Wait a second, that's also a difference of squares. And I'm noticing I have a difference of squares in the denominator, so let's just factor both of those. That will leave us with an x plus 1 and an x minus 1 in the numerator, in denominator an x plus 2 and an x minus 2. So actually, do we have any common factors? Nope. So there's going to be no hole in this graph, but it will have asymptotes. It already has a horizontal asymptote. We do still have two expressions, or two factors rather, in the denominator that, again, if those were 0, it would make the function fall apart. So that means we will have two vertical asymptotes, which we'll get from figuring out what's x plus 2 equals 0, solve for x, and same thing with x minus 2. And so our vertical asymptotes are going to happen at -2 and +2. And so this is the scenario where I'm going to go ahead and take a moment to figure out my x, my y intercepts. Let me actually change my color. Okay. So if we're looking at x-intercepts, keep in mind, any x-intercept is going to be where our y is going to equal 0. So in other words, I'm going to take my function, set it equal to 0, and then see what I can do to solve for x. And so if 0 equals 2x squared minus 2 over x squared minus 4, wait a second. If I tried to solve this out with the denominator and multiply through on both sides, my denominator is going to cancel out. So really, all I care about is what's going to make that numerator 0. Okay, so let's just do that. Okay, so let's solve for x. So add 2 to both sides, and then divide 2 on both sides. Oops, excuse me. So 1 equals x squared. But then when I take the square root of both sides, again, x is going to equal positive or -1. So I'm going to have two x-intercepts, one at +1, one at -1. If we're looking at our y-intercept, in other words, x equals 0. And so to find that out, I'm actually just going to go ahead and take my original function, plug in 0 for my x, and see what I get. So original function. So y equals, we're going to do 2 times 0 squared minus 2, and 0 squared minus 4. Well, those first two terms actually cancel each other out. 0 squared is just 0. So that leaves me with a -2 over -4, aka 1/2. So now we have all the info we need to be able to graph this out. Okay, first off, our horizontal asymptote is at 2. So horizontal line at y equals 2. Okay, we don't have any holes to worry about. We have vertical asymptotes. We have 2 of those, one at +2 and -2. So there's +2 and -2. And then we have, I'm going to go ahead and graph it in red just because it pops a little better on the graph. we have X-intercepts at positive and -1, and we have a Y-intercept at 1/2. And so it looks like I'm starting to write a little bit of or draw a little bit of a parabola almost. And in fact, that is exactly what would happen if we plug this in Desmos. Okay, and then just to make it look similar to a rational function, we would actually have 2 more branches, one at the top right and one at the bottom or top left. And again, if you're unsure of how I'm coming up with where these are sketched out, you could always graph this in Desmos. And in fact, we're going to practice that a lot more next lesson. Right now, all we need to focus on is how do we find horizontal asymptotes, holes, and vertical asymptotes. That should be our main takeaway from today. We'll look at the rest of our characteristics next lesson, but as always, let me know if you have any questions. And if not, go ahead and start on your practice.